Alright, so hello everyone. Today I'm back with another uh, post contest discussion, and this time it is Educational Codeforces Round 187, which happened yesterday. So we're going to discuss the first four problems of the contest. So let's begin with the first problem. According to the first problem, we have been given n identical boxes. The weight of each box is m, and durability of each box is d, right? So the problem says we need to construct. Okay, I'll just read it once. So to save space, Monocop wants to build several towers of boxes by stacking them on top of each other. Each tower will consist of a positive greater than zero integer numbers of boxes stacked on top of each other. To ensure that no box breaks, the following condition must be met. For each box, the total weight of all boxes above it must not exceed the durability of that box. And we need to calculate the minimum number of towers he can achieve, given that each of the n boxes must be used. So simply put, this problem gives us three integers. This is n and m and d. N is the number of boxes that we have, total number of boxes. M is, I guess, the weight. Yeah. So m is the weight of each box. And d is the durability of each box, right? So d is the durability of each box. And according to the problem, we need to build a tower of these boxes. So we can build a tower, like we can choose one box, then we can put another box on top of this, then we can put another box on top of this, and so on. Similarly, we can construct as many towers as we want, but the problem says we need to construct the minimum number of towers. Here it is written, we need to construct the minimum number of towers such that we utilizes all of the boxes, and the conditions that the weight of each box above it, the total weight. So if this is the first box, second box, third box, and fourth box, okay, every box has the same weight and same durability, right? So this problem says the weight of total weight of all the boxes above the current box, if that exceeds the durability, then the tower cannot stand. So let's say my durability was 40. So this is durability, and weight is, let's say, 10. So what I can do here is that I can place one box like this, then another box like this, another one, and another one. This is my first box, second box, third and fourth and fifth, right? So we can see that for the first box, the weight for all the boxes is same, but for the first box, the total weight above it would be 40, right? 10. These are four boxes with 10 weight each, so this is like 40, and since the durability is 40, this can hold. We cannot add yet another box on top of it, right? So this is the maximum height it can reach, and then we can do this for all. All the n boxes. There is a mathematical solution to this problem, but during the contest, I just brute force this. I initialized one, or I kept one box like this, and then I kept forming this tower until and unless my height was exceeded. So let's say I placed one of my box here, right? Then I decremented n by 1. So because I have placed my one box over here, now n minus boxes are remaining, and I can keep placing the boxes over on top of it, as long as the durability of all the boxes on top of it do not, or the weight of all the boxes on top of this particular box, so 2 3, as many blocks or boxes as many as we can put, we can keep putting, and then as soon as the total weight of these boxes exceeds this durability, then we can begin forming the new tower, right? So we can do that. We can brute force this because the constraints were low. It is only up to 50, so we can brute force this. So I'm taking NMD as an input. Count equals to 1 is the number of towers that I'll form. Total is the total weight. So total denotes the total weight on top of the current, the lowest star, right? Because the lowest box will have the most weight, right? The lowest box over here will have the most weight. If this is my tower, we can if my if I see on top of my second tower, whatever is my weight on top of second tower, it will be greater if I look onto the first one, right? So the weight of all the boxes on top of one will be greater than that of two, right? So I just need to look at the last tower, because this condition needs to hold that all the boxes on top of the tower, all of the weight of that boxes must be lesser than equals to durability. So we only need to check for the last box. So that is what I'm doing. So if I add the current, m was the weight, right? So if I add this weight to my current tower, and if that exceeds the durability, then I want to begin a new construction. So I begin a new construction, I increment the number of towers by 1, and I initialize my total by 0, because now we have begun forming another tower, and then the total weight above this box is now initialized to 0, and then we can keep doing this, right? And then we can output the count. So that's it for the first problem. I think it was pretty simple. Let's move on to the second one. So the second problem says, let's define f of x as the sum of digits of x. An integer x is considered beautiful if f of x equals to f of x. You're given an integer x. In one move, you can choose any digit in the number and replace it with another. The resulting number cannot have leading zeros. Your task is to calculate the minimum number of moves required to make the given number beautiful. Alright. So the problem says we have been given f of x. So f of x is the sum of digits of x, right? And so let's say we have been given this number 923, something like this. This is my number, and according to the problem we need to make f of x equals to f of x, right? So this the sum of this number, the digits of this number, the sum of the digits of this number must be equal to sum of that digit of number. So let's say I had a number like 1 2 4 6. So the sum of digits of these numbers is 6 plus 4 is 10, plus 2 is 12, and this is 13. And then the sum of all the digits of x was 13, and then the sum of digits of 13 was 4. So these were different. So this does not hold. And if I had a something like this, x was 101. So now the sum of digits is 1 plus 0 plus 1, which is 2, and then sum of digits is 2 again. So f of x is now equals to f of x. So now this is a valid condition. And now the problem says we can choose any digit and replace it with any other number, right? So we can do that, and we need to find the least number of operations so that f of x is equals to f of x. So that is what we want to do. So I want you guys to think in the direction when this condition will hold, right? F of x, when would this f of x would be equals to f of x? So let's just brute force this. Let's just check for some samples. When does this condition holds? So let's say I had something like 2794. The sum was 9 plus 9 is 18 plus 4 is 22. So sum of the f of x was 22. And now 22, sum of 2 plus 2 is 4. So f of x is 4. 1 minute, yeah, this is 4. So this is not equal. We can try for some other values. You can keep doing this, but you need to observe a certain pattern to decode this problem. According to the problem, to make f of x equals to f of x, we need to have the total sum of digits strictly lesser than 10, like 1034. So the total sum is 3 plus 4 7, and plus 1 is 8. So total sum is 8, and sum of this thing is again 8. So f of x is 8, and f of x is also 8. So now this condition holds, right? So essentially what I'm trying to prove here is that the number which have its sum of digits lesser than 10. So if my sum of digits is lesser than 10, then this condition holds. So this condition will hold that f of x would be equals to f of x. This is because the sum the total sum is lesser than 10, right? So if it is lesser than 10, then the sum of that thing would again be that particular thing, right? So if I had a sum like 9 or 8, whatever, when I add this element, take the total sum of this will be 9 itself, this will be 8 itself. Again, you can have for these things also. So 9 plus 0 plus 0 is again 9, and 8 plus 0 plus 0 is again 8, right? So that is my proof that in order to have f of x equals to, or this condition, we cannot have sum greater than equals to 10, because if I had 64, so the sum of the digits is 10, and then sum of this particular thing is 1, so 10 is not equals to 1, so this will never hold, right? If I had a two digit sum or 3 digit sum, let's say, so I had a sum of 32, let's say I have some number, let's say 9, 18, 27 and 5, so sum of these digits is 32, and then sum of this thing is 5, so this will never be same, right? F of x can never be same as f of x, because this thing changes once, and in order to for f of x and f of x to remain same, we cannot try to or there's just only one possibility, that if I have f of x is lesser than equals to, strictly lesser than equals to lesser than 10, then my f of x would be equals to f of x. You can take some time to digest this, but you can try to prove it in this way, that if I had if the sum of digits is greater than equals to 10, then the sum of that particular, or sum of f of x would never be equals to f of x, right? Because that is greater than 10, and sum of its digits would be somewhat different. So that is what I'm trying to prove. So we see that for the condition of f of x and equals to f of x to hold, we need to make the total sum strictly lesser than 10, right? So what can we do to reduce the overall sum lesser than 10? We can just keep in each iteration we can just take the greatest element and then remove that or replace that by 0, right? So if I had a number like 109326, so in the first iteration I could take this 9 and replace this with 0. So this will subtract minus 9, subtract 9 from the total sum. So the total sum was 1 plus 9 plus 3 plus 2 plus 6. So this was 15 on the 2021, and then you can subtract this 9, so this would be I guess 12. So now when you write this as 100326, this would be 12. Yeah, this is 12. So that is what I'm saying. In each iteration, just pick the largest element that you have and then replace that with 0. Now there's just one more catch to the problem, that it might happen that the first number itself is the largest, so you cannot replace the first number by 0, because the question says that you cannot have leading zeros, right? So here it is mentioned that the resulting number cannot have leading zeros, so we cannot take this 9 and replace this with 0. So what I'm trying to prove here is, or what I'm trying to say here is that you can choose all the elements you can. So I choose this 9 and replace this with 0, I choose this 9 and replace this with 0, and even if I had something like 2 again, so even after removing these two 9s, if my sum of digits is again greater than equals to 10, so then I will need to perform an operation over here, so I'll replace this with 1, not 9. So we'll not subtract a sum of 9 over here, I will subtract a 8 from the total sum, right? And that is all for the problem. We can do this. So we only need to take care of this particular case, that if I had multiple number of or if my first digit was, let's say, 5, and I had multiple 5s, and let's say we are in a certain iteration that 5 is my largest value. So the first number, which is 5, that should be taken at last, because this will be replaced by 1, right? And rest of the 5 will be replaced by 0. So I'm saying that let all the numbers except the first one replaced by 0. So we'll change this to 0 and we'll change this to 0, and at last, if my sum is again greater than or equals to 10, then we'll replace this by 1. That is what I'm trying to conclude over here. So we can do that, and I did my implementation with a priority queue. So I created a priority queue and a map, and I then just extracted all the digits of this number n. I got the digit, I pushed that to the priority queue, and here I'm checking if my I'm keeping track of this last digit, because whenever I encounter this last digit, I want to make sure that I take all of its occurrences, the later occurrences first, and the first number or the last number at the very last, right? So that's why I'm keeping my last number is n, and I have maintained a total sum over here, and I'm keeping the frequency, because let's say in my current iteration my largest number is 5, and if I had multiple occurrences of 5, then I will keep removing it. As soon as my frequency becomes 1, then I will change this to 1. Otherwise I'll keep performing on the later occurrences of this particular number. So that is what I'm doing while my sum is greater than or equals to 10. So while my total sum is greater than or equals to 10, we need to change this particular x. So that is what I do. I obtain the greatest digit from here, and if the greatest digit is the first number or the last number, then I need to check if the occurrences of that particular number is 1. So let's say I have a 9099 something after this also. So I chose this, and the frequency of 9 is 3. So I chose this 9 and replace this by 0. The frequency became 2. I chose this 9 and replace this with 0. The frequency became 1. And now when I obtain this 9, we can change this to 8, and the frequency will become 0, right? So that is what I'm trying to do. If my current the greatest number or greatest digit is equal to the last one, and the frequency of this particular thing is 1, then I will replace this with 1, because I have no other option. Otherwise we can just subtract the complete number and replace that with 0, and the number of operations is the count, right? And I decrement its frequency at the last, and that is it. I print the result. I hope you got it. It was a pretty simple problem. Just take some time to digest it. We'll move on to the third one. So third problem says you're developing a test generator. It takes two integers s and m as input. You need to construct an array of non-negative integers this is a1, a2, an, such that the summation of ai is equals to s. For each I, the condition ai and m equals to ai holds, where and is the bitwise AND operator. In other words, in each number ai, the bits that are set to 1 can only be in the positions where the bits in the number m are also set to 1. Determine whether there exists an array. If it exists, find the minimum possible length. So according to the problem, we have been given two parameters, which is s and m. S is the total sum of numbers, or total sum of elements of array, and let's say if my array was a1, a2, a3, so on till an. So then the use of m is, if I have formed this particular array, then this particular all the elements mod or not mod, all the elements when ANDed with m must be the elements itself. That is what is mentioned in the problem, that ai and m equals to ai holds for all I, right? So this holds for all I from 1 to n. That is what is mentioned in the problem. So first of all, let's try to digest what the hell it is written over here. So I want you guys to or to put it simply, you should know the concept of supermask and submask in order to understand this. We'll try to dig into it a little bit. So let's say if my AI is equals to 1 0 1 1 0 0 1, right? So I want to find such a number m so that these bits that are on in AI are on in the result itself, right? So if we want to obtain such a number in where the bits of AI are set and the result are also set, since we need to obtain the AI, when I end this particular AI with m, I obtain a AI again. So these bits must be set, right, for this particular thing. So I set all of these bits to 1. Now when I end this with, let's say this was AI and this was m, right? So in order to obtain AI and m is equals to AI, the bits that AI have turned on, m has to also have to be turned on, right? And m also, those bits have to be turned on. That is what I'm trying to say. And for the rest of the bits can either be 1 or can either be 0. We do not actually care about them. It could be 0 0 0 or it could be 1. It doesn't matter. But the bits that are on in AI has to be on in m, or in other words, the bits that are on in m or to put it simply, if you observe this particular pattern, the bits that are on in AI has to be on in m also, and the bits that are off in AI, that could be on or off. It doesn't matter. So when you look at this m, this AI is a submask of m, right? So if I had a bit like 1 1 1 1 0 1 1, so this is a mask, let's say, and the submask is where the ones are the ones can become zeros, but zeros cannot become 1. So any its submask could be when this 1 becomes 0, this becomes something like this thing. So this is a submask of this, or I can set multiple ones to be 0. So 1 0 0 1 0 1 0 again. So this is a submask of this also. So whatever m is given in the problem, right? So whatever I have as m, right, AI has to be a submask of that particular thing. That means the ones that are set in m, that could be unset in AI, right? But the zeros that m has, they cannot be turned on, because if let's say this was my m and AI was this particular thing, then when I AND this with m, right, this particular let me make this a 1 also. So this particular thing doesn't hold because of this thing, right? This bit AI and m has to be equals to AI, right? But if this bit was not set in m and it was set in AI, then this condition will never hold, because this will become 0, right? So that is what I'm saying. If whatever my m was here, the AI that we generate has to be a submask of that. Submask means the ones that the one or the set bits that I have in m. So these are set bits. They could be turned off. But the zeros that I have, they cannot be turned on. Yeah, because use your logic a little bit, right? If the zeros are turned on, right, then when I take this the end of this bit, it will be 0, and the bit of AI and the result will not be same, right? So zeros cannot be turned into 1, the ones can be turned into 0. This is a concept of submask. I hope you got it. Now we can see how to do this problem. So I want you guys to look for the monotonicity for this problem, because this is just basic monotonicity. So let's take the first sample. Sum is equals to 13 and m is equals to 5, I guess. Yeah, 5. So representation of 5 in binary is 101 raised to 13. The total sum is 13, and now we need to find the smallest length array such that the sum is 13 and ai and m is equals to ai for all I, right? So the valid construction for this is this particular array. The bits, I'm writing the binary representation below. The sum is 5 plus 4, 19 plus 4 is 13, so sum is 13. And when you AND this with m, so m representation of m was this, so this will be the number itself. So when you AND this would be 4, when you AND this would be 4, and when you AND this would be 4, right? So in order to solve this problem, if we can fix some constraint, because we cannot just think randomly if we are trying to solve this problem, because we don't have much to think about. We just have two conditions. So let's try to build the answer from these two conditions itself. If I fix some length x, right, I fix my length x, so can we determine that we can form a valid construction or a valid array in this length x? So if my length was 5 and m is equals to 6, let's say 4, and my length x is equals to 5, that means I have 5 elements in the array. Just stick with me for a little longer and you'll understand this perfectly. So now I have 4 bits because m is 4. M is not 4 actually, I'll write m as 8. Cool. So m is 8 now. M is 1000 in binary. So now I have, according to the ourselves, then we have fixing some length x. So we have fixed the length x and x equals to 5. That means that we have 5 elements, and m is equals to 8 means we have m as this thing, and we can have some mask of this particular m. So we have only one submask for this particular element, which is 0, because we can turn this bit off, and this is the submask. So alright, I'll take some other. So let's say my m was 9. Let's say this was, so m has become 9. Okay. So now I need to find if for a certain x, for a fixed x, can we generate a x length array such that the sum of its elements is s, and all of its elements and with m are the elements itself, or the element itself. So how can we do that? First of all, the elements that we try to put over here have to be a submask of this particular thing, right? So if my m was 9, the only possible submask for this particular thing is 1000 and 0001, right? These or we can have the number itself. So these are the only 3 possible submasks. 0 doesn't matter because this doesn't contribute to the sum, so it wouldn't matter. So these are the only 3 possible submasks of this m when m is 9. So either I can place this I have 3 possibilities to place this here, right? So now what can I do? So now we can construct this greedily. How? We have 5 places for each bit. So let's try to look this bit by bit, and I'll start with the leftmost or the most significant bit, because we need to minimize the length, right? And I can only minimize the length when I start from the last one, right? Most significant bit greedily. So also one concept is there, like if you choose this, if you have to choose 2 4s, then sum of this is 8, right? So if I had 2 bits on over here, I can just choose 1 bit which is left to this, right? So if I have 2 bits on the second position, instead of taking these 2 bits, I can choose 1 bit over here and it will contribute to the same sum, right? Instead of taking these 2 bits, because they were occupying 2 positions, we can greedily, if we have a space over here, we can greedily, instead of placing these ones over 2 places, we can place this one over here, right? So that is why I'm saying my greedy solution. So I start from the last bit, then I look if this bit is set in M, right? If this bit is set, so this bit is set, because for the bits that are not set, we cannot set them, because AI has to be a submask of M, right? Not a supermask. So zeros cannot be turned into 1. So that is why I start from the last, and if I and then I check, is my last value or the most significant bit 1 or not? So sure it is 1. So now I calculate, let's say my sum was 18, or not 18, this was 22, my sum was 22, right? Or yeah, we can do a 22. So my sum is 22, right? Okay, and M was 9. Now for the first position I check if my bit is set. Yes, sure, my bit is set. So I calculate how many these bits we can set, or how do I say it? Yeah, how many of these bits, these set bits, will need to construct our sum, So to do that, we can just divide the sum by this particular bit, right? So if I'm constructing this, I'm on this particular bit, the third bit, right? So when I divide this 22 by 2 to the power 3, which is 8, this results into 2. The floor division of this particular thing, this results into 2. So I can have 2 bits on for constructing my answer greedily, right? So I had 2 bits on, let's say. Rest of the bits I made 0. Now when I had 2 bits on, I've made a sum of 16 over here. 8 plus 8 is 16, so I decrement this 16, so I have now left with a 6. Now I check for this bit. This bit is 0, so we cannot make this one. Now we move on to this, the first bit. This bit is again 0, so we move on to the 0th bit. So now it is set, sure it is set. Now we'll check if we can construct our remaining sum with the help of these bits. So now, this is the 0th bit, so this will contribute to the 0 to the answer, which is 1. So how how many ones would we need in order to construct this sum? That is 6 over here. But since our length was 5, we cannot construct we cannot have or we cannot construct this like this. If my x was, let's say, 6, right, then what I can do over here is my bad, sorry. Now I have my length x is equals to 6, right? So now when I go to this last particular bit, now I can see that this bit is set. My m was 9, right? I'm sorry, I know it is getting a little confusing, but stick with me. So what I'm doing here is I'm checking from the most significant bit to the least significant bit, and I'm checking if my current bit is on or off, because if it is off, then I cannot make it on, right? Because the elements AI has to be a submask of M. So in order to have, in order for them to be a submask, the ones can be reduced to zeros, but zeros cannot be reduced to, or zeros cannot be changed to 1. So that is why I'm checking if my current bit is on or off. Now I'm constructing my answer greedily, because let's say if I had 4 ones over here, then if I had space, then I could, instead of placing these 4 ones over this place, I can place 2 ones over this place. And instead of placing these 2 ones in this place, I could place 1 1 in this place, and this will still contribute the same sum, because 4 ones over here were what? 2, 4, 6, 8. Instead of writing these 4 ones, I could write 1 and 1. Now 4 plus 4 is 8 again. Instead of writing these 2 ones, I could write a 1 over here, and this is 8 again. So the sum remains constant, and we take as less space as possible when we start from the most significant bit, right? So that is why we start from the most significant bit and go to the least significant bit. Now coming back to our original example, now I'm on the last bit, 0th bit. This will contribute what to the answer? 2 to the power 0, which is 1. So what is the remaining or how many remaining bits we have to turn on in order to or what is the capacity that we currently have, because we have 6 space and we have 2 to the power 0 capacity to add. So 2 to the power 0 into 6 is what our capacity is, or in easier words, sum by the remaining sum. This is remaining sum, 6 by 2 to the power 0. So this is nothing but 6. So if I set all of these bits on over in this particular bit, then I will have my answer. So I can construct my array as this is 9, this is 9, and rest of them are 1. So 9, 9, 1, 1, 1, 1. This is my final answer. You can see that 9 and 9 is 18, 18 plus 19 plus 20 plus 21 and 22. So sum is 22, and you can AND this with m, which was 9. So this is this thing. This is the sum mask of this. So this holds. So now if this holds for 6 length sub array, or 6 length array, I'm sorry, then this will also hold for 7 length, right? Because this will just be 0. The last particular case will just be 0, right? This will also hold for 8, because the remaining, the whatever is remaining there, that could just be 0, right? So that is what I'm saying. This is my monotonicity. If I can make a subarray for 5, then I can also make a subarray for 6. I can array for 6. I can also make an array of length 7 and so on till length whatever I want to make. So I need to find the minimum. So if I can make a array with length 7, then I know I can make with greater than that. So I'll shift my right pointer to over here. And now we find the mid, we check for the mid. If we can make for the 4, if we, let's say my x was 4, so I check for the 4 length subarray, 4 length array. I'm sorry, I'm repeating myself. But if my mid is 4, then I'll check if I can make 4 length array, and if I can, then I can make greater than that. So reduce this further, because we need to find the minimum length, and we'll go bit by bit and construct our answer. Because we can do this, because every bit is a multiple, or is a multiple of the bits writer to it. So let's say this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 3 and 4. So this is 16, 8, 4, 2, 1. So when you standard this particular bit, all the bits that are right to it are divisors of this particular bit, right? So 2 divides 4 and 1 also divides 4. So that is why I'm moving greedily from MSB to LSB, right? Because instead of taking 4 ones or 8 ones or whatever ones I need to make, I'll take the least count and move and take over here on this particular bit, so that I take least number of bits as possible, as minimum bits as possible, and I'm greedily constructing my answer like that. And that is it for this problem. I hope I was able to explain. This is the code. So this is my L and R. Answer is initialized with -1 in case if my array doesn't exist, and then I'm checking for mid. If for mid it exists, then it exists for the right, all positions in the right. So I'll decrement my R, otherwise I'll decrement my L, and I'll return my answer. As for the checker function, I have a remaining variable as S, and is my mid. So this is the length array that we are trying to make. We since x was till 118, that is why I'm iterating from the 60th bit. If my current bit is set, I'm this right shifting by this by the element that I want to check, or the bit that I want to check, and I'm checking if it is 1. Then I'll take this number. I've written a coin, because this is like coin denominations problem in the CSCS problem set. So we have been basically given some coin denominations, like we have been given this bit, we have been given this bit, and this bit. Let's say that is what we are given, right? We have been given some set bits. We can either take this bit or not take this bit. We can either take this bit or not. We cannot take the bit which is left, right? So if my set bit, if my m was something 16, 8, 0, 1, this thing, something like this, then I can take all the sub mask of this, but I cannot set this by, I cannot take a super mask, so I cannot take this 0 and make it a 1, right? So I have these particular coin denominations, and I need to find the minimum length array, so that by using these coin denominations I generate a sum s. I generate the sum s. So that this is what our problem is reduced to. And then I just check if my current bit is set. If it is set, then the current bit will be the denomination, or if I'm on the third bit, it will contribute 8 to my final answer. I could take as many 8s as we want. So let's say my sum was 34 and I'm on the 8th, and my I'm standing on the third bit. So this 2 to the power 3 would be 8. I could take 8 plus 8 plus 8 plus 8. So I can take 4 8. I could set 4 bits as 1. So this is nothing but divided by, or integer division by remainder by the current bit that I'm on, which is 1 left shift by the current bit I'm on. So this is what our number of bits would be. So this is let's say my x was 3. If my x was 3, then I can not take these 4 bits. I can only take these 3 bits. That is why I took a minimum of this thing with n, or the mid. So that is what is written over here. And then I could take this from the remaining, and then at last I just check if my remaining has become 0 or not. And that is it for this problem. I hope you got it. It wasn't that difficult to begin with. I'm sorry if I made it difficult, but I tried my best to explain this. And yeah, let's move on to the fourth one, the divisibility game. So I was trying to solve this today, and fortunately I could solve this, but I made a lot of wrong summations. Most were really, but anyways, I tried to explain this in simpler terms. So I have an array. So I have an array A, an array B. A is of length n and B is of length m, right? So according to the problem, Alice and Bob are playing a game. Alice goes first. Each player could take 2 numbers, so Alice can choose x and y, and Bob can also choose an x and y. Alice choose x and y such that y is divisible by x. So y is a factor, or y is a multiple of x. So y mod x equals to 0. And Bob chooses x and y such that y mod x is non-zero. When they choose this particular set of x and y, the y gets reduced. They choose x from the array A and y from array B, and then this y gets removed from this particular array B for Alice and for Bob as well, right? So if Alice chooses let's say some b1, b2, b3, so Alice chooses this particular element and pair this with some ai, then that ai remains as it is, but this b actually disappears and gets deleted. And now Bob deletes some number if he can, and Alice deletes some number if they can, and whoever player cannot make a move loses. So that is what is the given in the problem statement. Now n and m are small. I mean the values of ai and bi are small, just to say. And now we can observe this problem as Alice and Bob play their. I'm trying to put it in this way, that Alice and Bob are playing their own game, right? Because Alice chooses such numbers that are divisible. Alice will only choose such number where y mod x is 0, and Bob will only choose such numbers where y mod x is non-zero, right? Let's say if my A array was fixed with only one element, so A, let's say, was only 3, and B had multiple elements like 6, 9 or 12, 5, 7, right? So if my size of size of A was 1, so Alice and Bob only had one option to choose this element and pair this with whatever y they can. So in this particular example, Alice can only choose such numbers which are multiple of 3. So Alice can only choose 6, 9 and 12, right? And Bob can only choose 5 and 7, right? So in this particular case, I can claim that whichever if Alice has 3 possible answers and Bob has 2 possible answers or 2 possible values, and Alice has 3 possible values, then Alice would win, because Alice can play longer for longer time, and then Alice would win this game, or whoever has the more number of elements with themselves, they will win the game, right? So if Bob had 3 elements and Alice had 1 element, then Bob will win the game, because Bob can play for longer. That is I'm sorry, I actually lost my habit of trying to explain. I'm feeling a little tired now, but yeah, anyways, let's keep on moving. So that is what I'm saying. If my length of array is fixed as 1, then the Alice and Bob do not have much more options. If you look carefully, they only have limited option. Now if my array A has multiple options, so A1, A2, A3, A4, and array B has multiple options as well. Also, please watch this problem if you're specialist or above, because otherwise it is just a waste of time, because you might not know standard techniques like small SPF and how to generate factors of a number recursively and all these things. So if you're below 1400, please don't watch this problem, but yeah, let's proceed. So I have in this particular case I fixed my length of A as 1, but here my length of A is dynamic, like the problem says. Now let's try to keep a Alice bag of Alice and bag of Bob, like we did over here, right? These are the elements. The bag of Alice is 3. The elements in the bag of Alice is 3, and in the bag of Bob is 2, right? So let's now try to deduce the logic in the same way. Okay, so we can only delete the elements from set B. Okay, so I'm claiming that whatever element that I have in B has a divisor in A. So let's say I had 6 in array B and I had a 2 in array A. So Alice can remove this 6, right? Don't you agree? So Alice can take this 2 and pair this with 6 and then remove this particular element. So I'll increment the count in Alice bag by 1, so it will have 1 element. Similarly, for all the elements in the array B, I could just check if any of its divisor is present over here, or any of its factor is present over in the array. Since these AI is small, we can check that in order of 1 by creating an array, right, and storing the frequencies, right? So that is what I'm saying. For the elements in the bag of Alice, right, we can just iterate on the elements and keep iterating on the elements and see for all the factors. If any factor is present in array, then we'll increment the count in Alice by 1, right? Because Alice can choose these particular elements and remove them. So Alice has these many possible possibilities, right, to play the game. Now for the Bob, one thing we know for sure is if an element has no factors in array A, then Bob can remove it. Let's say I had a 7 over here in the B, and array A was 2, 4, 6 and 5, something like this. So this 7 cannot be taken by Alice because none of its factor divisors, which is 1 and 7, are present in array A. So then I'll increment the count in Bob's bag by 1. That is for sure. Other than that, Bob can also choose such elements whose some factors are not present. So let's say B was 16 and A had 2, 4, 6, 8 and 10, let's say. So factors of 16 were 1, 1, 2, 4, 8, 16. Although Alice can choose and remove this particular element, Bob can also choose and remove this particular element by pairing this 6 and 16, right? Since 6 is not a factor of 16, Bob can also choose these particular elements. So we know that saw that Bob can choose those elements for who's the divisors, for for those whom no divisors exist, and he can also choose such elements for which there exists at least one number which not divides this particular element. So how can we check that? We can check for all of its divisor that are present in array A. So what are the divisors that are present in array A? The divisors are 2 is present, 4 is present, 8 is present. But array A also has more elements present, 2 more elements. So 2 more elements that are present, and they are not divisors of array B, so that they have to be non-divisors of array B, right? So in that case also we can take this up and pair this into Bob's bag. So this 16 will also come into Bob's bag. And now once we have generated 2 bags for Alice and Bob, now we can simulate the game for M, because the length of the game cannot be more than M, since there are only M possible numbers for the B array, right? Now in Ellie's turns, now we have a catch also. Bob will have 2 bags instead of 1, because the numbers like these, right? For 16, Alice can also remove this and Bob can also remove this. So 1 bag for Bob is for that Alice can also remove this particular element and Bob can also remove this particular element. And then the rest for whom no divisors exist, they will be in Bob's bag, because Bob can only remove them. And for the elements where all divisors of it exist, let's say I have a 8 and all the elements exist in array A, so then Bob cannot remove this 8, so then this will be in Alice, and there would be one common bag from where both Alice and Bob can remove this particular element, right? So that is what I'm saying, there would be one common bag over here. Now in Alice's turn, Alice will try to pick from this bag first, because if Alice removes this particular element and not this, then Bob can eliminate one possibility for Alice, right? So Alice wants to keep as many elements that Bob cannot remove, because Bob cannot remove these particular elements, because these elements have all of its divisors present in array, and Alice cannot remove these particular elements. So they both want to maximize the numbers in their bags, right? So they will each try to remove from this bag first if they can. So in Alice's turn, Alice will see if there's something in this bag and then remove this. If let's say I had 2 elements over here, then Alice will remove 1. Then in Bob's turn, Bob will remove 1. Now Alice doesn't have a choice, so it will remove this thing, and then Bob will remove this thing. We can simulate this game now, and then that is pretty much it for this problem. So essentially we just need to find the total count of elements for Alice, Bob, and then common one, and then we can just simulate the game. So the implementation is a little trickier of mine at least, and I know there are easier solutions, but this is what I came up with. So this is the solution. I'm generating an SPF array in order to obtain all the prime factors and the power of those prime factors, or all the multiples of the particular element, factors of that particular elements. I'm taking nm and m as an input, and I'm creating this visited array so that I could check if if a divisor exists or not in array in order of 1. That is what I'm creating this array. I've written this cleanup because I have this global array visited. If I have for each test case I'm creating this particular array, then it will result into TLE. That is why I have a cleanup over here. Now Alice is the number of elements that only Alice can remove. Bob is the number of elements that only Bob can remove, I guess. Was it Bob 1 or Bob 2? Yeah, so Bob 2 was the number of elements that Bob can remove only, and Bob 1 is the common elements that both Alice and Bob can remove, right? So now I'm iterating on all the elements of B, and I'm creating this, I'm forming these bags, right? So please ignore this implementation, because I'm actually I was trying to first generate all the factors with sieve, but that caused time limit exceeded, so I had to do like this, just take a pause and read about this implementation. It actually generates all the possible divisors of a particular element by using the prime factorization using SPF technique. You can read about in blogs in Codeforces, I guess. And once you are done with this part, then just for those for those who don't know, you can just treat this as a black box, and then just imagine that this particular function is generating all the factors of a particular element in B. So I'm iterating on the elements of B. Then I check if the count of divisors of this particular element. So let's say my array A was 1, 2, 4, 6, 10, 5, 12, and array B was 6, 7, 8. So I'm checking for each of its divisors. So 6 divisors of 6 are 1, 2, 3, and 6. So I'm checking for each of its divisor, and if at least one divisor exists, then Alice can remove this particular element. So that is what I'm trying to do here. If at least one divisor exists, then I'll increment the bag of Alice by 1. If no divisors exist of this particular this element, so let's say I'm on 7, and since divisors of 7 are 1, let's say this one was not there, so divisors of 7 are 1 and 7, and both 1 and 7 are not present, so only Bob can remove this. So that in that case only Bob will remove this, and I increment the frequency by or increment the Bob's bag by 1. Otherwise, if it can be removed by both, so if it have some common factors from A and let's say if Alice can also remove this, that is if at least one factor of this particular element is present in array A, and there are some elements in array B which are not its factors also, so that means both Bob and Alice can remove this. So I'll increment the common bags by 1. So Bob 1 actually represents common bag, and now I just simulated this game. 0 stands for chance of Alice, and y is the total number of games. Now if x is equals to 0, that means it is Alice's turns, and if Alice is equals to 0, that means Alice can not make a move now. So I output Bob, right? Now this is Bob 1 was common bag, so Alice will try to remove from this common bag firstly. If it is non-zero, so Alice will remove from this common bag, and this common bag frequency will decrement by 1. Also this will store this in Alice. We would have stored this also in Alice, right? Because 6 was 6, both Alice and Bob can remove, so when we were constructing our answer, this 6 would have been present in our Alice also. So this we have to decrement that also, or you can write an implementation such that this 6 only counts 1 in the common bag. If Alice cannot remove or there's nothing in the common bags, then Alice will have to remove from the bag that Bob cannot remove, the separate bag. So Alice will remove from there. If it's Bob's turn, then Bob will see if Bob cannot remove from the common bag or cannot remove from the from his bag, then Alice would win, and then we'll return. Notice that I'm calling the cleanup function over here so that this thing, the visited array, gets cleared. Then Bob will again try to remove from the common bag if he can. If he cannot, then he'll take from his bag and decrement the frequency. Then I'm switching the choices. If none of these things get called, then the answer depends on the parity. Yeah, you can notice that. And I'll just print this if in case it doesn't get called, and I think this will never hit, but I just wrote it as a precaution, and I'm just if some return do not execute, then I'm just writing doing a cleanup over here, and that is it for this problem. The implementation got a little heavier, I guess, but I hope you got the solutions. It was a little hectic to record this record this stream, record this post content discussion, but yeah, I'll see you guys in the next one. And if I have provided some value, please forgive my teaching technique, because I'm still new and I'm not consistent enough, so that is one thing. And anyways, thank you for watching. I hope you got the solutions, and if you don't or if you haven't, then please let me know in the comments. And thank you so much for watching again, and Radhe Radhe.